All right. Okay, sorry, I had to get a couple of things ready over here. All right, well, good morning, everyone. So in the last couple of lessons here, I would like to go over the definitions of schemes and sheaves. I realized that we didn't quite get as far this semester as I was really hoping to. I was really hoping to get to sheaves at least a week ago, at least 2 weeks ago, actually. But we'll just try our best to kind of go through some of the definitions and what some of the different properties are here. So let's just do a couple of quick announcements. Friday's lecture is now on YouTube, so hopefully you'll be able to view everything there. I will have office hours. I'll admit at 11 a.m., I'm gonna be kind of in and out because I have a couple other meetings that I'll be having at 11, but still, if you have any questions, if you aren't able to reach me, just send me an email, because I'll certainly be checking email then. But I will be around at 4 p.m. for office hours later on in the day. And then finally, the last homework assignment, very last assignment, will be due this coming Friday. So I haven't posted it yet, but I'll try to get that up very soon. And just like the other ones, this here is just supposed to expand upon some of the definitions that we'll be covering in lectures this week. Okay, now in order to set up the general framework of sheaves and schemes, I want to review everything that we've done this semester, but I want to do it from a slightly different point of view. Essentially, I want to try, excuse me, I want to try to write everything so that we're actually defining all of our concepts in terms of a given integral domain. So let me review the definitions of affine and projective varieties, of the Zariski topology, and then the quasi-affine and quasi-projective varieties, now with respect to an arbitrary integral domain. So in everything that I say today, I want F to be a field, which I am not assuming is algebraically closed. Right, I'll try to point out the different places where we did assume that, but we are not assuming that today. Let's let R be the polynomial ring in n variables, S be the polynomial ring in n+1 variables, and this script O be any integral domain. So you might think of things like the integers as an integral domain, or even either one of these polynomial rings here will be an integral domain. So first, let's review the definition of affine n space. So remember that we before naively defined it as just a collection of n tuples where each of the coefficients here, a1 through an, are inside of our field K. Now, we actually have an embedding that sends us from an n tuple to a maximal ideal. And here I want to point out that notice that I'm using slightly different notation now. Right, so before when I wrote an of f, that was the collection of n tuples. Now when I write an subscript f, this here will denote spec of our polynomial ring in n variables. So up to this point, I've been saying things like we're going to abuse notation. Here now I'm going to be very precise. So again, the one over here on the left just means collection of n tuples, whereas the one over here on the right actually means the collection of prime ideals. And so we always have an embedding that sends our n tuples into the prime ideals. But over here for the prime ideals, this will be slightly more general. We can do something similar with projective n space. So remember before, we naively defined it as just a collection of these classes, equivalence classes, and we could do a very similar thing. Now we have an embedding that will send our equivalence classes over here to these homogeneous prime ideals. And remember that these homogeneous prime ideals satisfy the property that they do not contain here the irrelevant ideal. Remember that the philosophy of the irrelevant ideal is that this kind of corresponds to the origin. So what if my a1 ... an a0 were all equal to 0? But because here I'm staying away from the origin, then I want to say that it does not contain the irrelevant ideal, right? That's kind of the philosophy of us doing it this way. But again, we still have this embedding that allows us to send these tuples over here to these homogeneous prime ideals. So from here on out, I'm going to think of affine space over here as spec of our polynomial ring in n variables, and I'll think of projective space as proj of our polynomial ring in n+1 variables. Right, remember that the way the proj construction works is it's the collection of these homogeneous prime ideals that do not contain the irrelevant ideal. So proj NP is one example of such prime ideals, right? Then we define affine varieties as simply spec of an integral domain O. Right, so simple enough definition. Once we do this, then of course we can define O as our coordinate ring, and we'll define the dimension as just the Crowell dimension of this coordinate ring. Right, so notice that now we're just defining everything purely in terms of the coordinate ring. Finally, we'll say that we have a non-singular variety if our ring is Noetherian and integrally closed. So the nice thing is that now we can define things like, what do we mean by the dimension? What do we mean by being non-singular at a point? All in terms of properties of this integral domain O, right? We don't need any weird formulas or Jacobian matrices. We're defining everything purely in terms of what we have here is our integral domain. Okay. So let me give you an example just to kind of remind you where all of this comes from. Let's say that our integral domain actually comes from the polynomial ring modulo some prime ideal. Right, so remember that when we were dealing with our varieties in the affine sense, we started to take a look at polynomials and zero sets of polynomials. So because we're dealing with a Noetherian ring, our prime ideal here is finitely generated. It's only generated by a finite number of polynomials. And so then I can talk about the zero set of this prime ideal. And remember that this is before what we were defining as our affine variety, right? So just zero sets of a collection of polynomials. Well, now we have an embedding that takes this zero set, and of course it takes a point, and it'll think of this as this prime ideal. Right? Actually, it'll be a maximal ideal. And so now this allows us to think of this zero set really as sitting inside of the spec of the coordinate ring, right? So this is why we're generalizing it, because we always have this embedding kind of in the very naive sense, is how we started the course, but we definitely want to write down something slightly more general. So of course, we can do the exact same thing for projective variety. Now, instead of dealing with an integral domain, we'll specify that we want a graded integral domain. So of course, we'll write S of X as the coordinate ring. That's because we want to keep track of the grading. And we'll think of the dimension here in terms of the Crowell dimension, -1, again, because the grading here is kind of what keeps track of the fact that we're a little bit different. We'll say that our variety is a non-singular projective variety whenever our coordinate ring is graded, Noetherian, and integrally closed. So again, this is the really nice thing, that we can write all of our properties of this variety purely in terms of properties of the integral domain, right? We don't have to deal with things like derivatives and Jacobian matrices and explicit formulas. We can write everything in terms of the ring. So as an example, just to remind you where all of this comes from, let's say that our homogeneous coordinate ring really is coming from these homogeneous polynomials modulo some homogeneous prime ideal. Right, so here I'm writing the F tildes as perhaps the homogenization as our original polynomials. And just like before, we have an embedding. So we have this zero set in the projective sense, and we can send here a point over to this maximal ideal, but I have to be a little bit careful. I really want this homogeneous prime ideal, right? So actually this is the typo, this should be proj MP, right? But over here now I have this nice homogeneous prime ideal. So we're going to generalize going from the zero set over here in the projective sense to actually proj of our coordinate ring. So all of this is what we mean by an affine variety and a projective variety. Now, before we can even talk about things like quasi-affine and quasi-projective, we have to talk about the Zariski topologies. Remember that we had this idea of what does it mean to be open inside of something. So first, we'll say, if we're dealing with an affine variety, that a subset is Zariski closed if we can find an ideal J so that our set V looks like the zero set of J. Now, this is hard to kind of translate directly from what we were doing before, so I'll try to explain in just a moment. But now what we're doing is we're matching up Zariski closed subsets with ideals. Not just prime ideals, but ideals. Roughly speaking, remember that prime means that it'll be an irreducible closed subset. But if we just have an ideal, we can still talk about closed subsets. So here now, I want this to be the collection of primes in spec O that contain J. So again, this is what we mean by a Zariski closed subset. It looks like that there is some ideal J, so that V is just the collection of primes that contain J. So using the lattice isomorphism theorem, or if you will, the fourth isomorphism theorem, this is equivalent to saying that V should look like spec of O mod J. So now you can see that I'm going to say that something is Zariski closed if it looks like spec of some quotient ring, O mod J. Right, that's going to be the philosophy here. So we'll say that a subset now, of course, is Zariski open if its complement is Zariski closed. So once we have this, then we can write down the standard properties. Both the empty set and the whole affine variety are Zariski open. If you have an arbitrary family of Zariski open sets, then its union is Zariski open. And finally, if you have a finite family of open subsets, then its intersection is Zariski open. So I'll leave a sketch of the proof for these in the lecture notes, but I'm not going to go over these in lecture today. It's really not that bad. Essentially, you just take these four cases and you just write down the right ideal J that's associated to everything. Okay. So again, Zariski open now, we have these properties. And of course, this allows us to define the Zariski topology. So if you wanted to know now, if someone gives you an integral domain O, here's how you define a topology. Now, this is actually, I think, one of the most beautiful things of algebraic geometry. That typically, when you're dealing with maybe a class in topology, you have to talk about things like Euclidean distance, and you have a metric, maybe even have a norm on the space. You can then talk about distance functions and how far apart things are. You can talk about a topology in that sense. And then, of course, eventually you talk about a slightly more general sense of things like a topology coming from open sets. Well, here's a really crazy idea. This says, if you give me any integral domain O, then I can define a topological space on that. Right, so again, if you give me any integral domain, I can define for you a topological space. So here's the crazy thought. Take the integers. The integers is an integral domain. According to all of this, I can define a topology on the integers. Right? And if you're kind of wondering what is that topology, remember that this is basically what we did as one of the homework assignments, that the open sets mean that it either looks like the whole set, so this will be spec of Z, or you take spec of Z minus finitely many points. Right? That'll kind of be the philosophy. Okay. Now, if you wanted to go back to what we've done so far in this course, then let's go back to the example of maybe when O looks like the polynomial ring in n variables modulo a prime ideal. Well, then again, going back to the lattice isomorphism theorem, every ideal J is in the form T mod the ideal Ix for some ideal T, and actually T has to satisfy this double inequality. So now we're just using the lattice isomorphism theorem to say that we can talk about this set T, and that should correspond to this ideal here, J. Right. And so now we can just write down a similar diagram to figure out how everything matches up. So remember that we have this map that allows us to say that any point can be identified with maximal ideals. That's essentially this bottom row here. Right, so this bottom row is what we just said at the start of today's lesson. You'll notice this one here in the middle, X, which is Z subscript the zero ideal. Here you have to kind of go back up to the definition here at the top. So what if J here is the zero ideal? Well, the zero ideal is contained in every prime ideal. So if J is the zero ideal, then this here is just X, it's just spec O. So that's where this here is coming from, right? So again, X here is just spec of the integral domain O, and this bottom row here is exactly what we said a couple of slides ago. On the other hand, let's say that we do have R subset T satisfying this here. Then of course, we do have this embedding, because if it's the zero set of a set T, then it's definitely going to be the zero set of the smaller set Ix. This is because remember that our Z's, that the order gets flipped around. If Ix is less than T, then Z of T is greater than Z of Ix. Right? That's one of the properties we proved about the Z thing, is that kind of the order gets reversed if I go from larger to smaller. Well, the top row here is exactly what we had from before, because now this just says if I have a point P, I can associate that to this maximal ideal MP. So I can embed the ZT over here into this V. But remember that this is kind of what we're used to intuitively, that we really want to say something is closed if V looks like Z of T. Right, so this here just basically says exactly what we're used to. So intuitively, we really want to think of V here as equal to Z of T. But now, if we use the third isomorphism theorem, then we really see that V here is really just the same as spec of R mod T. Right, really this is the same thing as spec of O mod J, but when you kind of invert and multiply, then this is just the same thing as spec of R mod T. Right, so I can really think of the elements of V as just looking like the maximal ideal modulo T. So again, I'll think of X as Z of the prime ideal Ix. So I could think of V as Z adjoin or Z of this set T. But this diagram here kind of explains how we can really generalize and piece everything together. So I am not going to worry about Zariski closure of a projective variety because all the definitions are very similar. But today, just to kind of focus on intuition, I just wanted to focus mainly on affine varieties. Okay. All right, so any questions up to this point here? That's defining the Zariski topology for an affine variety. Okay, all right, let's keep going here. So now that we have the Zariski topology together, now we can easily define a quasi-affine and a quasi-projective variety. Quasi-affine is exactly what you expect. It's a non-empty subset of an affine variety that is Zariski open. Right? That's the simple definition of a quasi-affine variety. Once we have that, then we have to be a little bit careful to define the Zariski closure. And the way that we'll do this is as follows. Given a quasi-affine variety, let's define the Zariski closure in this way here. It's Z adjoin I of U. Or if you don't like that, you can say that it's spec of OU. And this here is an affine variety that contains U. And now I have to give you a couple of definitions here. Well, IU is that prime ideal that's the intersection of those primes in U. Right? Remember that U is a subset of spec of O. So the elements of U are actually prime ideals. So here now, I'm going to intersect over those prime ideals contained in U. So that's what I mean by IU. And you can convince yourself that based on this definition, that this U bar here actually contains U. Right? It's just a matter of kind of sitting at the definitions and staring at it a little bit. But again, if IU here is defined as this intersection, you can prove using this definition here that U is contained in U bar. So because this is the prime ideal, then we see that the quotient here, this coordinate ring, is an integral domain, which actually means that this Zariski closure is closed, right? That is that it really is an irreducible variety, so it really is an affine variety. Right, so it's a little trick here, but this still does work out. So again, if you're given a quasi-affine variety, we'll define this ideal here as the intersection over the primes in U. Then we can define the quotient here as the coordinate ring of U. And then we can define here U bar as just this, in a sense, the zero set here of IU, right? The Z sub IU. In a very similar way, a quasi-projective variety, call it U, sitting inside of a projective variety X will be said to be quasi-projective if it's Zariski open. Right, same ideas before. Just like before, we can define the Zariski closure, call this U bar, where IU is now a homogeneous prime ideal, which is the intersection over those homogeneous primes in U. Remember that U here is contained in proj O, so everything in U is a homogeneous prime. So because IU is a prime ideal, we can look at its quotient, which we're going to call here SU, and we see here that this quotient is an integral domain, which is also a graded ring. So that's why we have over here proj of SU. So again, the whole thing here is that once I look at the intersection over the primes in U, then I have a nice ideal that kind of controls everything here that I care about. Now again, this is the crazy thing. I'm simply looking at this integral domain O, right? Not introducing really a whole lot of fancy topological methods. I'm doing everything purely using commutative algebra. So before I go any further, I wanted to give some history behind what's really going on here, because you'll notice that we kind of started with things like affine varieties, then we kind of went on to projective varieties, and we were discussing curves, and then we eventually just jumped completely into commutative algebra and generalized all of this. So before we go any further, I wanted to kind of show you the genesis of where things were coming from, so you can kind of see where we're heading next, how mathematicians eventually came up with all of these concepts. Well, I think it's fair to say that a lot of this really got its start in the modern language in 1857. There was a German mathematician by the name of Bernhard Riemann. If any of you have heard of the Riemann hypothesis, this is the same Riemann. He actually worked a lot with complex functions, and these are really functions that are differentiable. So nowadays we call these analytic functions. So he really wanted to know more about the domain of definitions of such functions. And he eventually called these Riemann manifolds. And kind of the nice case that typically we care about these days are typically what are called Riemann surfaces. Anyhow, he wanted to understand the space of analytic functions on a Riemann manifold and relate that to the space of differentials on a Riemann manifold. So in calculus, you might think of a function like y equals f of x as being differentiable, but then of course, if you want to integrate such functions, you have to talk about things like f of x dx. So the f of x dx will be a differential, and then the analytic function, the differentiable function, will be f of x. So he really wanted to understand how these two are related. It turns out he actually proved a really nice inequality that kind of relates everything as vector spaces. And essentially it says something like how the dimension of the space of analytic functions is related to the dimension of the space of differentials. And he actually used all of this to define the concept of a genus. But he was only able to work out an inequality. He wasn't able to prove that, say, something is equal to something else. Think of maybe like the formula from linear algebra of the rank nullity theorem. That's the formula that tells you how the rank of a matrix is related to the nullity of a matrix. But here, he can only prove an inequality, not a straight equality. Well, about 8 years later, his graduate student, Gustav Riemann, actually proved a more general statement. He actually made the inequality precise. He made it an equality. And because of this, a lot of people put the two names together, the student and the teacher, and we nowadays call this the Riemann-Roch theorem. So this was one of the theorems I was going to cover, but I'm not going to have time to cover this here in this class. But I'll say that if you are interested in it, I definitely recommend looking up the Riemann-Roch theorem as best you can, and I'll be happy to answer any questions in case you'd like to learn more about this theorem as well. I'll point out here that you'll notice that they passed away in 1866, although Gustav Riemann proved this theorem in 1865. It's actually a really crazy story. Riemann proved the theorem in 1865, and about a year later, Riemann, the advisor, took ill with tuberculosis, and he actually passed away in July of 1866. Well, as a bizarre twist of fate, about 4 months later in November 1866, Riemann also passed away of tuberculosis. So they both passed away, same disease. They lived in different parts of Europe, but they also passed away a year after they made this really famous theorem that the two of them are really well known for. So it's kind of a bizarre story here. So now let's fast forward about 35 years later. The German mathematician David Hilbert proved his Noether-Satz. Remember that this is the zeros theorem. So remember that what he wanted to do was ask the question, if you're looking at the ideal generated by an affine variety. So remember that here's where you take an affine variety, that's a collection of points. You then ask about the polynomials that vanish at these points, and then you form this ideal that we were calling I of x. So what he wanted to know is, what's the least number of generators you need for this thing here? This is kind of the idea of the Noether-Satz. So he really proved that this I of x really should be a radical ideal, that it should look like, the radical of some prime ideal. That's kind of the rough idea. But he was only able to work over an algebraically closed field F. So notice that he still made a little bit of progress because Riemann and Roch worked over the complex numbers, and Hilbert was able to work over a slightly more general sense. In fact, Hilbert was able to say that he didn't really have to work with these funny thing of manifolds by looking at analytic functions. He was able to generalize slightly by looking at algebraic functions. Think of this as saying we're going from things like e to the x to polynomials, right? That's kind of the idea. So he was able to really generalize things quite a bit. Well, now, inspired by the work of David Hilbert, there were two other German mathematicians, Emmy Noether and Wolfgang Crowell, who were able to develop the theory of commutative algebra to try their best to generalize what David Hilbert had done. So for those of you who are used to being in Millikan, one of the classrooms in Millikan is named after Emmy Noether. So this is the same Noether here who actually did a lot of work in coming up with a lot of these ideas in algebraic geometry. And if you remember when I mentioned about the Crowell dimension, this is the same Crowell, the same Wolfgang Crowell. So Emmy Noether and Wolfgang Crowell did a lot of work by setting the foundations here. So a lot of what I'm saying today really came from their basic ideas of saying that maybe the right thing to do is to look at spec of an integral domain. This is why we talk about things like Noetherian rings, that's named here after Noether, and you can talk about the dimension of a variety by looking at the Crowell dimension of the ring. This is all named after Wolfgang Crowell. So a lot of this was done over the span of about 2 decades, through the 1920s and the 1930s, but there was a lot of foundational work that was done here. Well, this foundational work was built upon for the 2 decades following by a handful of other people. One is, I believe this is a Dutch mathematician named Van der Waerden, and Andre Weil was people say he was a French mathematician, but I believe he was actually from Belgium. And also Oskar Zariski, who actually was a Russian mathematician. So remember that Zariski is eponymous with things like Zariski topology. So really the three of these individuals here really worked to push the foundation more in commutative algebra. They actually went from defining affine varieties to defining the much more general sense of quasi-projective varieties. So really it was the 1930s and 40s that we actually saw everything that we did today completely built up. And really it was these three individuals here, Van der Waerden, Andre Weil, and Oskar Zariski. I should point out that they did not assume that you had to work over an algebraically closed field, because remember, now once you do everything in terms of commutative algebra, you don't need polynomials anymore. All that you need to say is if O is an integral domain, you can work out everything in complete generality. I also want to point out here, you might be interested to look in the dates of when some of these individuals were born and when some passed away. See here, Noether and Crowell were really born in the, I'd say the second to last century, in the late 1800s, but now by the time you get to Van der Waerden, Weil, and Zariski, essentially now they're being born in the 1900s. So you're starting to see a generational shift in terms of how people are doing things here. But I do want to point out that now, over the span of almost 80 years, we've gone from looking at the complex numbers to now working over a totally arbitrary ring. In the 1950s, there started to be a school of French mathematicians named Bourbaki. And some of you may have heard of Bourbaki. It really wasn't any one person. It was really a pseudonym that was given by a group of mathematicians. I believe in the 1950s or so, there may have been about 10 to 15 mathematicians. What they really wanted to do was put all of mathematics on a firm foundation. You know, you may ask very basic questions such as, well, what is a set, right? The funny thing is that no math book will define for you what a set is, because it turns out that sets are actually very complicated. The sets really run into some really nasty problems. Well, the Bourbaki folks actually knew that this was an issue, and this is why they started to work out a lot of the stuff from first principles. So if you ever wondered whether mathematics is on a found footing, it actually is, because the Bourbakis actually made sure that everything worked out. So in particular, there were a couple of French mathematicians and one Japanese mathematician, so Claude Chevalier and Jean-Pierre Serre. They worked hard to try to figure out what is the idea of a scheme. And of course, this is what we're going to go over today. There also was a Japanese school that was starting to be built up in the 1950s. So this is, of course, post-World War II, where there were a lot of Japanese mathematicians who were working in Japan. They also came over to the US, and that there was a lot of work done now through the French school and the Japanese school in algebraic geometry. But I do want to point out that some of the names that you'll see here, Chevalier, Serre, and Andre Weil, that all were members of Bourbaki at the time. That leads us to 1960, which was the groundbreaking year for algebraic geometry. There was a very strange figure named Alexander Girlthe, who was a Belgian mathematician, who wanted to completely generalize everything. Now, when I say generalize everything, I really mean generalize everything. He really thought of all of mathematics as kind of a special case of algebraic geometry. So he wrote a series of books. One here is his treatise, which if you translate the French, it's Elements of Algebraic Geometry. And he really wanted his best to found a firm foundation in which you can solve a lot of these problems, set up a lot of these definitions. So in this book, in 1960, Girlthe defined the concept of a scheme. So here it actually took about 100 years or so for us to get up to this point, going from the Riemann-Roch theorem to the idea of schemes. But I wanted to point out that this really went through a lot of different revolutions. First, it started with the with the German school. There actually is an Italian school that I didn't mention here, but eventually it did move over to a French school. And nowadays, the philosophy of algebraic geometry is heavily, heavily influenced by French mathematicians. The funny thing is there's still a lot of groundbreaking papers in algebraic geometry that are in French that have never been translated over to English, because the philosophy is everything has already been done in French. There's really no point to translate it over to English. Just learn French if you really want to understand algebraic geometry. So any questions here on the history that I've tried to set up? Okay. All right, so let's try to get into some definitions here. Well, remember that if we're given a quasi-affine variety U, that really means that U is contained in some affine variety, call it X. And remember that we defined the Zariski closure by looking at this intersection over those primes in U. I'm going to use that as motivation for defining something new here. Right, so again, we're going to use this intersection over the primes in U to try our best to define the Zariski closure. So let's try our best to exploit that to write down something more general. Now, given an integral domain O, let me define the quotient field as the following. So the quotient field of O is literally the quotient of elements from O, P over Q, but I want to make sure that the denominator does not equal to 0. So for example, if O here is the integers, then K here, of course, is just going to be the rational numbers. Right, so that's just what I mean by the quotient field. So I have a theorem here that I want to give you. Let me denote P of X as the power set of X. So this is the collection of subsets of X. And by subset, you can think of that here as U. Similarly, let's denote P of K as the power set of K. So these will be the subsets of our quotient field K. Now I'm going to use this to define a function that I'm calling OX that's defined as follows. Once you have U, then you can define OX of U as the intersection over those primes in U. Right, so here I'm taking the intersection and I'm intersecting over the following sets. So by O sub I mean this subset of K. So here's the subset such that the denominator is not an element of the prime ideal I. Right, so again, remember that U is contained in spec of O, so the elements of U are prime ideals. So I can talk about what does it mean for Q to not be in the prime ideal, the denominator. So of course, 0 is in the prime ideal, so Q is never equal to 0, so this is okay. Similarly, I can talk about now the intersection of these sets as I intersect over those points I that are sitting in U. So this is what I'm defining as OX of U. So there's 3 properties that I claim here. Number 1, this set, OX of U, is actually an integral domain. Right, so this OX of U here is an integral domain. Number 2, let's take a look at the extreme cases. What if U here is the empty set, and what if U here is the whole set X? Well, my claim is that if it's the empty set, then the set here is just the field K. Right, so this is how we recover the field K. If U here is the whole set X, then this OX of U now is just the integral domain O. Right, so these are my 2 extremes. The final thing is that if U is contained in V, remember that U and V are just subsets for the moment, then OX of U contains OX of V. Right, notice that now the inclusion gets reversed. Right, so again, if U is contained in V, then OX of U contains OX of V. Right. So let me make a couple of remarks here. This OI is called the localization of O at I. Right, so that's just the name. It's the localization at the prime ideal I. Actually, let's take a look at this set M sub I. So M sub I is a set where the numerator lies in the prime ideal I, but the denominator does not. This actually is a maximal ideal of OI. So it's a maximal ideal, and it turns out that it's actually the unique maximal ideal. So there's only one maximal ideal sitting inside of this localization. That's why we call it a localization, because it's only just kind of one place. So we typically call this a local ring, right? Because it's a ring that has exactly one maximal ideal. So if I were to talk about spec of OI, that would just be MI, right? It wouldn't be too surprising, it just would be MI. So again, we're gonna go back to this concept here of intersections. And now we're gonna try our best to define this thing here. Right? So I wanna quickly go over the proof of this before we call it a day here. So let's start by showing the first one. Why is it that we have integral domains? Well, remember that this OX of U is contained inside of a field K. So that means things like it doesn't have any zero divisors because the field doesn't have any zero divisors. I also know that my operation is going to be commutative, it'll be associative, so on and so on and so forth. So I'm going to use something like the subring criteria to make sure that it really is a ring. Once I know that it's a ring, I just get for free that it has to be an integral domain. So I really have to prove three things. That I'm dealing with the non-empty set, that is closed under differences, and is closed under products. Right? That's like the subring criteria. Once I check these three, then I basically am done. So let's do the first one. Well, the number 1 is never in any prime ideal. So this ratio has to be in OX of U. So that means OX of U at least contains the multiplicative identity. What about number 2? Well, let's pick an A and a B, right? P over Q. So I can write the difference here in this way, right? Like PQ divided by QQ. So all I really have to prove now is that QQ, the denominator, is never in I. So to prove by contradiction, say that it is. Well, because I here is a prime ideal, then either Q1 is in I or Q2 is in I. But that's a contradiction because that was the whole point. The way that we choose this is that the denominators are never in I, as long as I is an element of U. Right, so that proves the second one. And the third one is very similar, right? If A looks like P over Q, B looks like P over Q, you can look at the product, so that's like a PP over QQ. And just like before, I know that Q times Q is never an I. So we're done there. Okay. So what about the second statement? So this is the whole thing about the two extremes. Well, if U is the empty set, then really the conditions are vacuous. Because remember I said something like you intersect over all the places in U. Well, if there's no places in U to choose, then there's really nothing to check here. So you just kind of get this as just like a vacuous definition. Again, there's just nothing to check. On the other hand, what if U is equal to the whole affine variety X? Well then, if I want to show that we have equality, I need to show that O is contained in OXU and OXU is contained in O. I have to do these two different directions. For the first direction, let's say that A is in O. Well then, of course, A, I can write this as P over Q, where P is A and Q is 1. Right, just write it as A over 1. But 1 is never an I, so we're done. Right, so this thing here really is in this OX of U. Right, so the first direction is actually kind of easy. For the second direction, it's a little bit trickier, but not too bad. Pick your P over Q, and remember that Q is never an I. So what I'm actually going to do is show that Q is a unit. Here's the rough idea. Consider the ideal generated by the denominator. If this were a proper ideal, then it would have to be contained in a maximal ideal, but every maximal ideal is prime, and therefore we would conclude that Q would have to be contained in a prime ideal. But that contradicts this assumption here. So this actually means that this ideal generated by Q is equal to the whole ring O, but then that actually means the Q here has to be a unit if that's the case. And so then P over Q makes sense because then 1 over Q is just lying in O again. Okay. And then the last one, 3, is just actually very easy because this just says that if U is contained in V, then you just pick an element in OX of V that has to be an OX of U. And I'm not going to worry about going through the proof of that because it's not too bad. So we've set up all of this now as kind of motivation for what we're going to do next time, which is formally define a scheme, and then we'll formally define a sheaf. So I know that it's a little bit late, so do you have any questions for me here before we call it a day? Okay, well then let's maybe go ahead and call it a day. So the next time I do want to go over some aspects of category theory to begin with, but we are going to spend the whole time going over what a sheaf, a stalk, and a germ is. Right, and we'll try our best to go over some examples as well.
All right, thanks, Professor.
Hey,
Thanks, Professor. Have a nice day.
Have a good rest of the day yourself.